Good morning, everybody, and thank you very much for joining us this morning. We've had a huge registration for this webinar, which I think speaks to both the importance and the interest around this subject matter. We will be, next slide, please, Sarah, apologies. Thank you. We will be recording the webinar, and the recording will be available on our YouTube channel shortly after transmission. And then we'll also share the slides with you. I just wanted to say a little bit about the project that's brought this webinar to us today. It's called Cornwall Flow Commission. It's funded by Shared Prosperity Fund through Cornwall Council. The lead partner is Celtic Sea Power, and my colleague Phil Johnston from Celtic Sea Power will tell you a little bit more about them in a moment. And then with ourselves, Offshore Renewable Energy Catapult as the partner. The project was put together specifically to leverage everything we've researched, learned and developed over more than 6 years in this space to ensure that we maximise the value of an industrialised scale floating offshore wind in the Celtic Sea, with particular emphasis on Cornwall, as this is funded by Cornwall Council. So next slide, please, Sarah. If I say a little bit about Catapult. So the Offshore Renewable Energy Catapult is the UK's leading technology innovation and research centre for offshore renewable energy, by which we mean wind, wave and tidal. As you can see, we have 8 regional centres, with our Floating Offshore Wind Centre of Excellence up in Glasgow, our Test and Validation National Facilities in Blyth, our Operations and Maintenance Centre of Excellence in the Humber, and then the people that are bringing you this webinar today are mostly based in Hale, and we work very closely with our Welsh colleagues in our Pembrokeshire office. Next slide, please. So the objectives of this webinar, we wanted to introduce what's happening currently, mostly under Celtic Sea Power, about regional characterisation work. We want then to look at how innovative technologies can accelerate consenting, and what gaps there are and what use cases we would be looking at. Then to introduce the concept of a regional ecosystem monitoring programme, and to look at the data requirements, including the analysis and accessibility. So next slide, please. We have a really full agenda. We're not planning at the moment on Q&A because you'll see how full it is. But what we would ask you to do is please put your questions into the Q&A or the chat, but preferably Q&A, and we'll marshal those after this event, and we'll answer them either individually or in themes as is most appropriate. If we do have time at the end, we'll pick up a few key questions, but I think that will be later. So the agenda, as you see this, I'm Julie Taylor, Innovation Manager for the Offshore Renewable Energy Catapult. I lead on various regional issues around the Southwest, and specifically lead on our national programme Accelerating Consenting for Offshore Renewable Deployment, ACCORD. I'll be handing over to Phil Johnston, who's Business Development Manager of Celtic Sea Power, and he also has a background in marine autonomy systems. And he's kindly standing in for a colleague today. From there, we will move to our Dr. Caroline Worley, who's Catapult's environmental specialist. Caroline has authored 2 major reports, both of which will drop into the chat later on in this webinar. One on accelerating consenting and one on regional ecosystem monitoring programme. Caroline, in turn, will hand to Professor Beth Scott, who's Professor of Marine Ecology at the University of Aberdeen. And her research portfolio includes very well-known projects, including Pelagio, Predict and Econex. Beth is also a co-director of the EPSRC Offshore Renewable Energy Supergen Hub. Beth, in turn, will hand to Benjamin Williamson. Dr. Williamson is an associate professor at the University of Highlands and Islands, and he leads an energy research group looking at ecosystem effects of offshore renewables. Next slide, please. From there, we'll move to sort of hone in on the innovative technologies, starting with our own Dr. Melissa Sanderson, who's our principal R&D engineer on robotics. Melissa's passionate about designing complex robotic systems for real-world challenges. Melissa will hand to Dr. Tom Culverhouse, who has a PhD in experimental astrophysics, and his focus with Sonodyne lies in the application of novel sensing and monitoring technology to combat the marine community's main challenges. From Tom, we'll move to Nikki Harris, who's kindly joined us from SAISH. Nikki has been in offshore renewables and oil and gas for nearly 20 years, working on some of the largest offshore projects in the UK, Europe, and the States. And finally, before coming back to myself for a summary, Brijesh Surawanshi, who is our lead data engineer, who's working both in this environmental monitoring space, but also in operations and maintenance, will talk to us about data. So as you can see, you are in exceptionally good hands today, and we have a very full agenda. So welcome, and I'd like to hand to Phil.
Hello, everybody. Thank you, Julie. And firstly, to apologise for not being Harrison or Neil, who are the experts here, and it's their work that I'm presenting at late notice. But yeah, I'll lean on my background a little bit, but I really can't do too much because they've covered so much in the last three years of this programme. So I'll start though, because not everyone is familiar with. So next slide, please. With a quick précis of Celtic Sea Power. Basically, we are a slightly unusual fish, but we were set up with something called the Green Reserve, Cornwall Council, to really invest in the region ahead of floating offshore wind in the Celtic Sea. Recognise this huge kind of opportunity that could pull us along. Actually, we were on the ground to set things up to push into that, lean into that, across broad themes of industry, infrastructure, workforce, and environment. So a small team, but we live and breathe the Celtic Sea. I think it's about 17, 16 now, but live and breathe the Celtic Sea flow every day. But we're not limited to flow. We are, across other energy sources. But the fundamental goal is to maximise the social and economic benefits of and environmental of clean energy opportunities in this region. So that's what we do. I think there's another one as well. There we go. The environmental theme, which Neil has led on, is about accelerating responsible and sustainable development of Celtic Sea flow to protect and enhance the environment. So quite ambitious, quite bold, but that's what we do. We've got an eye bit of freedom to do that, and we've been able to push at doors that haven't otherwise been pushed, or doors that things like strategic thinking, regional characterization to environmental monitoring that have been in the air for some time. People have said that would be a good way to do it. There's precedents, as Caroline will talk about in aggregates and elsewhere. Can we do it afresh in offshore wind and this green field site of the Celtic Sea? So moving on to the next slide, please. Hopefully, yeah, and I think this is just a slide to reiterate. I will also skip through the last 5 slides because that's the detail, which isn't my strong point. That's what Harrison and Neil kick in, so I have to ask them afterwards. But this is really to kind of collate some of the noise that's around this. There's a lot of, I think it's fair to say, there's a lot of agreement in this area. Things that need to happen, need to streamline the licensing, need to streamline the consent, need to bring it down from 4 years to 1, is it, or however many years it is. We find ourselves in a system that's feeling the strain of it. Technology is clearly, while we're here today, it's clearly a key part of driving that reduction in time. But it's also, I'd ask the question, how consenting can accelerate technology. So I'll talk about data standards and approach to data sharing, which gives a clarity. So it makes it agnostic to the platform and the sensor that collects the data. If they know what's collecting to, what's the actual information, rather than collecting data for collecting data's sake. So move on to the next slide if we can. Here we go. So this has been Neil's driving force for about 3 years now. I think we set up in 2021, so it's nearly 4 now. So essentially working across collecting data ourselves, filling gaps, building a baseline of environmental evidence. That's the driving force. Through that process and seeing the bigger picture, we've convened lots of strategic partners. I know we're hearing from Poseidon later, so we're early in that engagement and trying to bring that forward in terms of, okay, understanding events, gaps, pinpointing where future activities can be focused and operate across the Celtic Sea basin. We've also, since I think last 2 years, Neil's been running a project which is about governance across international boundaries. So we can learn lessons from Ireland and Europe and elsewhere and look at the governance piece of that. But the key link is this regional environmental project, which I appreciate has a few other names and acronyms, but it's been in the air for some time. People talk about what they've done in Holland over the years for offshore wind. It's been validated in recent times by the Crown Estate. I think it was in November they came through with the route map. So that felt pretty good for our team here who've been doing it since 2021. And I'll touch on the evidence that the data that's come through from that in the next slide, please. Next slide, please. Oh, attention. There we go. Okay, so this is an overview, and after this, I've got detail I will whip through, but I'll happily defer you to the experts, and also I'm sure it will dovetail nicely what Caroline will talk about as well. But the data campaigns we've run to date have been one of the first things we did was put 2 FLIDAR buoys out there. So this is to collect wind resource and also metocean. In the cracks, we also realised that we could do things like eDNA in the survey and the servicing of that. But fundamentally, we put two buoys out there. This was at a point where we had, I think at one point, 20, 30 developers circling, looking at the Celtic Sea, most of whom, or many of whom, were contemplating putting these systems in to really kind of prove that it was windy out there. It is. And also show their investors. So it's kind of showing activity. They're active in the region. They're taking the Celtic Sea seriously. But actually, is that the most efficient way forward of putting half a dozen developers putting FLIDAR buoys out there that collects data that is then kept in commercial confidence? You know, that is a real challenge in this. So in many ways, the innovative thing that Neil did here was not to put the FLIDAR buoys ahead of the market, was to share the data and broker a data sharing agreement. It's got various strictures to it, not least because we've got, last count, I think a dozen, maybe 15 developers signed up to that as a data sharing agreement. It's a mechanism, but basically the data strengthens the regional model. So it's the kind of the complete pinnacle of this characterization approach. It allows that actionable data, that actual information to arrive from the data earlier, and for it to be shared, to share and accelerate informed decision making. So that was really key through that process, and also the aerial surveys, which is and it was a lot of this was seabirds. It links to some of the FLIDAR because we're looking at airborne LiDAR for flight heights of birds. Also can spot marine mammals, which is annoying for me, but that you can spot them from the planes because they're quite big. And also the Holy Grail, trying to match that to eDNA and subsea acoustics. Again, a similar theme of collecting data and doing it at a broad scale. So not site specific as it would be for a individual commercial development, be able to do it over an entire region. One of the questions that really posed up early on was resolution. So if you could do it over a broad scale, you want to do it as far as you can, and you want to do it as fine resolution as you can, but realistically, you find yourself there's an element of finding a compromise. But within that, you can sort of forge a data standard. I know that experts later on, and certainly those involved with Poseidon and Crown Estate, will be more on top of that. But that seems a really strong approach to me, because if you've got some data standards and the survey standards, it opens up what's interesting to me in my previous career was how you can collect that data commercially, speculatively. So you've already got the data's in hand. So, for baseline evidencing, the sooner you start repeating it, the better, rather than the sort of hurry up and wait model we have and piecemeal model we have at the minute. So that's what we've done. In the next few slides, I can whip through the detail, but conscious of time, but next slide, please. And oh yeah, this one. There we go, just to show where we've been and where we're going. So that's the kind of more described areas there between the tip of Cornwall to Pembroke and up to Ireland. That's the current PDAs leasing rounds for 4.5 gigawatts the next few years, the next year, in fact. And out there is the direction of travel for future rounds. But skip on another slide if we could, just to give you a little hint of detail, the results that's come through on the bird site there. So as it kind of highlights the data sharing agreements I mentioned, the airborne LiDAR and digital aerial surveys. Do get in touch for information. As I say, we hope it to be an ongoing program. And the next step, if we could get at least 2 or 3 slides, I'm afraid, I did say I'll whip through these for Julie's timekeeping, is to highlight the subsea stuff, because I can see a couple of names on the list who might be interested in where my old life has taken me. Yeah, another slide or 2, please. So these are for speed readers and those who are happy to contact us for more information. There we go. So we're getting into the work of it there. You see putting out a subsea network of acoustic recorders, and that's happened. We've won that through the Crown Estate, the Offshore Wind Evidence for Change program with Crown Estate. So we'll be able to put subsea acoustic monitoring out there in the current state. And being Neil, it's entirely logical, which means it's also entirely ambitious. That's working with the University of Exeter as well, and the Catapult as well on the project too. So Matt Witt, if you know him. So yeah, look out for that one. I think I can see at least a couple of names on the list who'll be interested, if not already involved. So there we go. That's the slide I was looking for. Yeah, it's ambitious. You know, it's as those who know about acoustics know, it's that evidence base is incredibly hard to capture and incredibly hard to keep repeating and pluck out if there are particular species of interest. So as well as the baseline data, this is a pretty greenfield site. So if there are fin whales or if there are beaked whales out there, we'd rather know that earlier in the process of consenting. So there's a kind of we can think about how that approach might lead to mitigation, for example. So there we go, eDNA as well, which is obviously a big part of that future. But conscious of time, I have to wrap up and urge you to contact us for any further questions. Thank you. So Caroline next, I believe. Caroline Wally from the Catapult, who's been working with Neil on this, on the regional characterisation piece.
Thank you, Phil. Hello, everyone. I'm going to talk to you about some of the work we are doing at the ORE Catapult. Next slide, please. Next slide. In July 2023, ORE Catapult released a report on accelerating offshore wind. It explores how smart technology could streamline data gathering, analysis and decision-making to help accelerate the consenting process. This was followed by a report released in November last year, which explores how a regional ecosystem monitoring programme enabled by innovative technology could benefit the broader offshore renewables industry as well as the environment. Next slide, please. So why do the reports come about? Well, if we take a look at the statement here, we realise some changes need to be made in the consenting process for offshore wind. It takes about 2 to 3 years to construct a wind farm. That's a wind farm of about 150 fixed turbines. Yet it takes about 5 years to get consent, but it's often longer. Now, the first report discusses the current consenting process, the measures proposed by the government to help accelerate consenting, and what part ORE Catapult can play in reducing timelines, which I'll now discuss. Next slide, please. So following on from the first report, we developed the Accord programme, which stands for Accelerating Consenting for Offshore Renewables Deployment. And the reason being, there is a need for more research that takes advantage of innovative technologies to better understand the functioning of the UK marine ecosystems within which large-scale offshore wind deployment is situated. A sound evidence base is essential to inform policy and marine management responses and provide confidence to regulators on guidance and data requirements for environmental impact assessments and habitat regulation assessments. So Accord is a 4.5 million 4-year joint industry project to accelerate offshore consenting process using smart technology and autonomous systems to reduce time and costs, enable more accurate data collection, lower the carbon footprint, and improve decision making. So next slide, please. So what is ORE Catapult's role? So we've so far completed 2 audits on available platforms and sensors. This is both UK and global technology and was completed by Plymouth Marine Laboratory. Platform audits were conducted using different categories such as size, payload capacity, autonomy level, whether they've been approved by the Maritime and Coast Guard Agency, cost and technology readiness level. The sensor audits were assessed by Receptor Group, resulting in a database of all technologies and included acoustics, cameras, electronic tagging and tracking, and biomonitoring tools such as eDNA. We also carried out a regulatory landscape review, examining existing and proposed legislation and regulations regarding autonomous systems in UK waters and airspace. So we now need to support the existing work that is being done to demonstrate and validate the effectiveness, accuracy and robustness of new technology. We are engaging with the statutory nature conservation bodies and policymakers to ensure new technologies can be confidently incorporated into EIAs and post-consent monitoring plans. We're engaging with developers, scientists and marine stakeholders to establish a network of innovators working in developing marine monitoring technology. Ultimately, we want to de-risk the consenting process by creating greater certainty in the data collection. We believe that this uncertainty and the resulting delays in receiving consent can be improved through better monitoring. Next slide, please. So how might we improve things? Well, autonomous solutions now exist for many of the relevant monitoring challenges, and they already offer the potential to streamline some operations. Data of direct relevance to environmental monitoring for offshore wind can be collected using acoustic, visual and oceanographic sensors deployed on marine autonomous systems. There is considerable potential for both cost savings and a substantial improvement in the temporal and spatial resolution of environmental monitoring. Now, the next few slides will just give you some examples of use cases showing current methods versus new ways of monitoring. So currently, seabird, whale and dolphin populations are counted using light aircraft observations. Generally, this is done once a month for 2 years, but is limited to fair weather conditions with nocturnal species not accounted for. We are advocating replacing aircraft with beyond visual line of sight drones combined with marine autonomous platforms integrated with acoustic detectors. We can increase coverage of monitoring, increase confidence in the data, and reduce overall cost and carbon emissions. Okay, next slide, please. So if we look at the benthic habitat, oh, sorry, go back. If we currently look at the benthic habitat, data is collected via seabed grab samples and drop-down cameras deployed from large vessels, whereas we can deploy autonomous underwater vehicles with photogrammetry capabilities that can cover 25 hectares a day at centimetre resolution. We can assess megafauna and habitat classification. We can combine this with side scan sonar and multi-beam echo sounder with eDNA analysis. So the major perceived limitation of autonomy in monitoring is the general inability to collect physical samples, particularly in the case of seabed sediments. These issues may well be surmountable, though, through re-evaluation of appropriate monitoring indicators and by the rapid technological advances that are currently taking place. Okay, so next slide, please. So phytoplankton is a key component of the marine ecosystem that's usually left out of conventional monitoring programs, and it plays a vital role in feeding larger marine animals. Now, as we look to deploy further offshore into the highly productive shelf seas, our need for more understanding of the effects of offshore wind, both stratification and this receptor group, are crucial. We can monitor in situ using water drones with autonomous underwater vehicles, water quality sensors tethered to fixed platforms, alongside monitoring vital physical parameters such as temperature, salinity, pH, nutrients, dissolved oxygen, to help explain any possible changes in the distribution and abundance of species. Next slide, please. Okay, so the second report that was released in November last year documented a framework for a regional ecosystem monitoring programme, or REMP. I'll run through the recommendations in that report and how it feeds into what we are discussing today. So there's a need to overhaul how offshore wind development sites are monitored, shifting from project-level EIAs to regional scale monitoring, which would remove overlap and duplication, reduce project management costs for developers, and improve the accuracy of cumulative impact assessments. It would also help to address the resourcing issues that hinder the organisations responsible for regulatory decision-making. Regional refers to the collective project development areas as designated by the Crown Estate, as well as the wider zone of influence, which includes impacts outside of the development footprint, the proposed cable route corridors and grid connections. It would be government funded, but hosted by an independent facilitator, such as Asphalt or a larger environmental consultancy, and costs would eventually be recovered indirectly in the tender from the winning bidder, which is how it's done in Germany. So we are advocating removing the scoping phase from the pre-application stage. Regional advisory groups instead would be established to engage on environmental engineering concerns in collaboration with key experts from academic institutes and statutory consultees. So current monitoring has provided a large amount of data on environmental effects at the species level, considering the sensitivity of potential disruptions to distinct receptor groups, such as marine mammals, birds and fish. It is essential that a monitoring plan for offshore wind farms is designed to detect changes within the ecosystem at multiple spatial and temporal scales. Ecosystem-based monitoring can be used to monitor the biodiversity and functioning of an ecosystem, including changes that may occur due to offshore wind development. So as part of suggested changes, we will look to adopt an ecosystem-based approach to monitoring that is driven by key indicators and monitoring priorities specific to each region. We would transition from current monitoring methods to make use of innovative technology. Compared with traditional in situ observations by ships and moorings, the greatest strength of autonomous platform networks is their capacity to conduct multi-scale and cross-disciplinary measurements. Such resolution is critical for a regional scale monitoring programme. Data sets and model output should be open access to ensure information is genuinely useful and that can feed into other policy and management measures, such as good environmental status and marine protected area assessments that promote sustainable development of the marine environment. Next slide, please. So the science is ready. We have the technology available in many respects. We just need the main players on board now. These conversations are being held, they are ongoing, but we just need the financial backing to support the programme. We're in talks with DESNZ, Great British Energy, and the Crown Estate on this and are hopeful. But up until now, all work has been funded by the Area Catapult. With our funding, our first plan will be to set up the regional advisor groups and develop a monitoring programme that is fit for purpose, ecosystem-based and hypothesis-driven to allow us to deploy offshore wind with the greatest confidence we are sustainably developing the marine environment. We want a multi-sensor, multi-platform approach that has the interoperability to harness real data in real time. The benefits of concurrent data collection methods utilising mobile and static platforms greatly increase the information needed to explain variations in seabird, fish, and marine mammal distributions, and provide robust, informative outputs that can help to reduce uncertainties and ultimately offer the best opportunity to understand and accelerate the sustainable future of the offshore wind industry. Next slide, please. So thanks very much for listening. Now I'll hand over to the brilliant Professor Beth Scott from the University of Aberdeen.
Hello, thank you, Caroline. Okay, so I'm here today to talk about the reasons why we need this, the ecological reasons, because we're obviously sitting in this trilemma of the biodiversity crisis, climate change, and energy security, and we have to do this all sustainably. So, if I have next slide, please. So I'm going to cover a lot of things, and note this is a two-part talk. I'm just doing the first bit, and then Benjamin Williamson will pick up the second bit on how we do this. So I'm going to rattle through rather quickly these reasonings why we need to change to our current approach. I'm going to show a couple of examples of mobile animals and the aspects of oceanography. I'm going to talk in particular about the changes to environmental impact and cumulative impact policies, and I'm going to give you a quick example of ecosystem approaches in our Pelagio project. And then I'm going to hand over to Benjamin to show exactly how. Next slide, please. So I think we all know, probably on this call, I call it what we deal with, the 3 Ds of environmental impacts of disturbance, displacement, and death. Next slide, please. And what we really need to move towards is our new, as I call them, 3 Cs, the cumulative effects, climate change, and compensation. Whereas the environmental effects actually depend on the level of certainty. So you heard already about all the surveys that are being done. It's looking at animals in space and over some time. But actually animals move around a lot, and a lot of things to do with displacement and death can actually be most sensitive to the spatial distributions. And so when we move to the 3 Cs, this is where we really need to understand why. What are the drivers of mobile animal use of their locations and their foraging habitat? And if you click again, please. So what we're trying to say is that we really need a better understanding of space use. Get this increase in certainty for our 3 Ds and provide new methods for the 3 Cs. Next slide, please. And so I'm showing an example then of some older work, but I think it's incredibly relevant of where we went to look at where animals are grouped as forager, where are the spots in space that are really important to a wide range of animals. And what we found way back when was that this is evidence of what you're seeing here in the picture is that we went along with some scanfish up and down. So we've got continuous information on the physics and the biology of these areas off the Firth of Forth. And what we found, what you're seeing in color there is the subsurface chlorophyll maximum levels. And what you're seeing then on the top here is our super predator, where we put all these animals together as biomass. And we can then look at where we saw predictably lots of animals is where we saw areas of subsurface high production. So as Caroline said, the chlorophyll, the plankton is really, really important. This is one way to find out about it. But if I can get the next slide then. What we're also trying to do is what are the instruments that can help us find that? Because what we're finding is the reasons you had lots of plankton in these really patchy areas, some of the reasons are internal waves where you get water flowing over banks or troughs. And in this picture, what you're seeing is turning up the gain on an EK60, an acoustic instrument. You're seeing the above warm water is colored blue, the below water below the thermocline is colored yellow. And what you see is these fingers of this internal wave that comes along. And what we see is that fisheries acoustics is good at not just finding fish, but finding these kinds of physical features. So next click, please. And what we can see then is actually when the physics changes, the fish change. The fish change their behavior very much through spring neap cycles and stronger neap tides and spring tides. So we really need to understand this behavioral aspect to understand linkages through the trophic change. So next slide, please. And so what we're trying to show is that we absolutely agree with everybody as ecologists, we really need to decrease the environmental risks, and we really need to decrease the time to consenting, because the environmental risks of climate change are by far our worst enemy. And so right now what we have, though, is we have these EIAs that are very much, as been shown, these long timelines, and this idea that we're doing one thing at a time. It is just not working when we look at the reality of what's going to happen in terms of space use. So next slide, please. So our solution then is this change in policy, that we also want to say you cannot add up multiple developments and get cumulative impacts the way the methods are done right now, because they are looking at single species. They don't put climate change effects in there, and especially this habitat change effect. Wind farms will change habitat. And you also, a lot of times you don't have the effect of fishing changes, which will be huge. So our solution is then these ecosystem approaches, that we can look at all developments at once in this regional approach that is being talked about today. We need to look at all the trophic levels at the same time, this simultaneous collection of data, but we also need to bring in aspects of climate change and habitat change and effects of fishing. Next click, please. And because there's a little animation here, what I get often is, no, it's too much. Ecosystems are too complex to understand. You know, we need to stay at this single species approach. But if I could have the next slide, please. So I'm just going to spend a couple of minutes saying that actually marine ecosystems are simpler than terrestrial ecosystems. They are highly predictable through physical forcing. So what I'm trying to show in these images is the fact that when you look at time and space, physical events in the marine world go quite linearly with the trophic levels as we go from primary plankton up through to whales. And as I was showing that actually looking at primary production, we can really easily predict where our predators might be. And that's so that because of the physical forcing in marine systems, that we can go straight up to ecological indicators from the physics. So next slide, please. So what we've done with that information is we've said, well, actually, looking at this paper that came out from Durrell, and this is what we've all been working on for a while now, is that not only are there going to be bottom-up changes from the structures, but actually the wind energy extraction themselves is going to change mixing and therefore going to change production. And we really need to take those aspects into account, because going back to my other earlier points, this sort of thing may very much change distribution of animals. So that wonderful work you're doing in figuring out the distribution of animals, they may change because of this. So the next click, please. So what we've done then is we have said, okay, this is where these big eco-wind program came about, and the scientific community pushing and pushing. And the one where I'm running called Pelagio, which is really trying to then look right from the physics to these ecosystem effects of wind farms. Next slide, please. And so what we're trying to say in a nutshell is that we can predict responses through physics to predator, that we know there's some response between physics and fish, that fish are being moved around, as I showed you earlier, by the tides, times of months, this sort of thing, seasons. Of course, birds are eating fish. So what we'd love to be able to do is go straight from the physics to things like birds and mammals. Next slide, please. And so what we've done then, we've put a lot of work into this for the last 5-6 years on our ecosystem models. How to do this then, how to take the effects of the physics and run it through all of the trophic change. and do this also including the changes in commercial fishing that will occur when fishing is moved around in areas, especially with floating wind. So we can put all of these aspects in, and we can predict out the population trends of all of these different trophic change with these approaches. Next slide, please. And what we've tried to do then is produce quite a few papers in quite a few different ways, speaking to a lot of different audiences, how we can integrate these approaches and look at our Marine Strategy Framework Directive and the good environmental status policies, how we can integrate these. And I've written multiple papers with a lot of my group, and this one in the middle actually is directed at engineers to really bring all of this stuff in one document. Next slide, please. And so what we've also then has been wonderful to work directly with Catapult just recently and look at the fact that there's sort of colliding approaches coming together from the ecological community and the Catapult community to move this regional approach with these hypothesis-led campaigns. And what we'd also like to put out there is we think we can also think about using this as some way of looking at strategic compensation. But I'll leave it at that for now and just say that there's also a scoping report out more about collecting physical data that has just come out. And then my last slide, if I get to that, is going to pass over to Benjamin Williamson, where I'm showing that we've been working together for many years now, more than a decade, where we're trying to look at these methods where we take the oceanography, fine-scale oceanography surveys, and especially these upward-facing instrumentation and the acoustics that I think from all of the things I've seen already today, that is what's missing. And here, where we can go from the physics to the prey to the predators, it gets less and less expensive to do it if we can get it from the fish. So I'm now going to pass over to Benjamin to show more exactly how we do that. Thank you.
Thank you very much, Beth. Really useful to set the rationale and the scene for why we're collecting these data sets. So as Beth talks about physics through to fish as prey and through to top predators, I'll talk for just a few minutes about how we collect these biophysical data sets across trophic levels to explain and predict environmental interactions all the way through to cumulative effects of large-scale ORE. Next slide, please. We base a lot of our measurements around using acoustics, and acoustics often from seabed platforms. And so this lets us take measurements 24/7, irrespective of visibility or illumination. We can take measurements throughout the water column at relatively low power, so we can fit these onto autonomous platforms. And it's also quite easy to automate the analysis of these, so we can quickly build up a perspective from large data sets. So on the left-hand side here, we're looking at an imaging sonar data set where we mount the sonar on a seabed platform, faces up through the water column. It pings several times a second and lets us build up an understanding of animal movement, behavior, measurements throughout the water column, interactions with seabed or ORE structures, and also predator-prey interactions. So on the left-hand side, the movement and behavior, here we're tracking a target using the rainbow color scheme over time. But then we often synchronize the imaging sonar for behavior with upward-facing multi-frequency echo sounders. And so that's these narrow cones on the right-hand side, where we repeat multiple pings over time. And again, through the water column from the seabed up to the surface, it lets us build up an understanding of what's in the water column, measures of biomass, and again, predator-prey interactions. So here we're seeing a school of fish near the sea surface and diving seabirds foraging on that school of fish. In this case, the seabirds validated with shore-based ground truthing observers. What we're interested in is how can we automate the detection, tracking, and classification of targets. And the echo sounder also allows us to use the frequency response of schools of fish to infer species. It's an example of herring at the bottom right of the screen. Next slide, please. And so we integrate all of these different sensors onto autonomous seabed landers. These can be larger platforms, the example you saw on the previous slide, or much smaller versions that you see in the picture here, getting ready for deployment in the North Sea. These are self-contained, so they can record for multiple months. They use onboard batteries, onboard data storage, and onboard processing. And that allows us to conduct baseline measurements, but also comparative deployments. So we can put these in different areas of a site, a reference area closer to infrastructure, to try to understand how are all of the effects that Beth talked about changing around offshore renewable energy. Again, we combine these different instruments, so upward-facing acoustics for pelagic fish, zooplankton as a measure of prey and prey availability, as Beth talks about. We can also integrate passive acoustics, so this lets us understand vocalizing cetaceans, marine mammals, but a measure of noise and the soundscape as well, with broadband recorders. And then using an ADCP, typically for measures of hydrodynamics, particularly interested in the wakes of these structures, I'll talk about later on. And then also basic oceanographic measurements, or a fluorometer to understand chlorophyll, primary productivity, and a CTD massed on the platform as well. And we're interested in the fusion of all these different instruments and also edge processing as well. How can we process the data on board to make informed decisions about monitoring, use of battery life, and even through to management? Next slide, please. So this is an example of the kind of data sets that we can collect. On the right-hand side here, we're looking at a vertical histogram of the distribution of schools throughout the water column per hour over a multi-week deployment. And what we're looking at here is next to a seabed turbine structure versus a reference area, a back-to-back deployment with no turbine structure. And here what we're showing is there's nearly twice as many fish around the turbine structure as the bottom plot compared to the top plot, but also the vertical distribution changes. The animals are much lower in the water column, and at low speeds, below 1 meter per second, we've got nearly 6 times more schools in the wake of the turbine structure. That's the blue bars. And by combining these acoustic measurements with the other measurements that I showed you on the previous slides, it lets us start to investigate why is this happening. Is it the structure effect, a fish aggregating device effect, but also the wake effects of these structures as well, using the hydrodynamic measurements. And by using multi-week, multi-month persistent monitoring from seabed landers, we can also understand the predictability of these prey aggregations and how's the prey available to top predators and might we be affecting top predator foraging behavior. Next slide, please. So Beth mentioned the Pelagia project, which is looking at physics through to ecosystem level assessment, offshore wind, fixed offshore wind. And this is an example as we've just wrapped up our 2nd year of field campaigns around the Sea Green wind farm in the North Sea, where on the left-hand side of the schematic, we deployed some of the moorings that I showed you at different ranges from an individual wind turbine, but also from the Sea Green wind farm as a whole. So at 50 meters, up to 500 meters, up to 3 kilometers, and comparing measurements in the tidal wake through to in the wind wake and at increasing range of the wind farm. And we use the same combination of upward-facing acoustics and onboard hydrodynamic measurements. What we could also do here is complement the multi-month persistent seabed moorings with a few days of ship-based surveys using similar instruments in a downward-facing manner. And by building up an understanding of the predictability of prey and the mechanisms that are driving it, it then allows us to use relatively few days of ship-based measurements could eventually be replaced by autonomous or uncrewed platforms to understand what's the gradient, what's the range of effect from the wind farm, and also build in seabed observers. And then at a greater scale, again, we complemented this with oceanographic gliders, the wider Pelagia consortium. Next slide, please. And whereas the first slide I showed you had just a few minutes of a data set of diving seabirds foraging beneath the school of fish, with the multi-month seabed landers, we built up this much longer term data set. And so here, this is the work of Julie Salvatat at UHI, processing these upward facing data sets. And here we see over repeated 24-hour tidal cycles, the dial vertical migration, zooplankton up to the sea surface, like that, but also fish schools interspersed with this. And what we're interested in is the availability of these fish schools to the top predators. Next slide, please. So Pelagia talked about our last 2 years of field campaigns, and now I've got just one slide on where we can go next with this. So we start to think about distributed sensor nodes, the scale of developments and measurements that are required, perhaps from Phil's introductory slides as well. And so this is some work with Simply Blue Energy and Ørsted in the North Sea, deploying these landers, but smaller versions to characterize new offshore wind sites. Again, using a similar range of instruments, but also starting to develop the data analysis and processing pipeline as we start to think about these distributed sensor nodes and how can we coordinate measurements especially deployments across comparative habitats. As Beth mentioned, there's much more explanation of this in our ICES paper from last year, led by Natalie Isaacson. And last slide, please. We're also working on floating offshore wind, and so this is some work from Caitlin Harris working on the iFlow project, which is looking at what's different around floating offshore wind. How's floating offshore wind affecting the distribution and behaviour of fish and marine mammals? Caitlin's just finished her second field campaign around high wind Scotland, working with Equinor in the North Sea. And what we're looking at here is there's a rapid expansion of floating offshore wind planned. It's a deeper, further offshore, potentially more productive shelf seas, potential for greater interaction with fish, fishing. What's the predator-prey interactions around floating offshore wind? Have we got similar prey attraction or elevated prey densities around these structures? What does that mean for top predator, particularly marine mammal foraging, potentially with greater prey availability, but maybe also with increased noise, perhaps from the dynamic moorings? So the iFlow project is in its final year, but we're just starting a much larger project called EcoFlow Equify, which will then expand this and start to build on a lot more oceanographic measurements as well, combining passive and active acoustic measurements. So next slide, please. Just a chance to say thank you very much for your interest today. I'm sorry I had to go so quickly, but if you're interested in future collaborations, future applications of the technology, how we might apply this to new environments, or even the technology development, sensor fusion, data processing pipelines, please do get in touch with Beth and myself. With that, I'll hand over to Dr. Melissa Sanderson from the Offshore Renewable Energy Catapult. Thank you.
Thank you, Benjamin. Hi, everybody. Yep, Melissa here. I'm a principal R&D engineer of robotics at the Offshore Renewable Energy Catapult. I actually sit within our research and technical capabilities, so very happy to speak with you all today. Next slide, please. So for today, I'll start with a review of the robotic platforms that are suitable for environmental monitoring and consenting of offshore wind farms. And subsequently, the platforms we'll be looking to support in our Accord program that my colleague Caroline just spoke with you all about. I'll then move on to an overview of the testing and demonstration assets at ORE Catapult, in which you can test your robotic platforms, including work that my team have been undertaking designing an offshore wind farm simulated environment just for robotic developers. So excited to share that with you. Next slide, please. Oh, okay, so now that we have discussed Accord's program goals and its potential to, build and bolster a new market sector, let's dive into the robotic and autonomous systems that will be critical in accelerating the consenting process. So first platform I'd like to discuss are autonomous underwater vehicles, or AUVs. These are ideal for seabed mapping, benthic habitat assessment, metocean data collection, and supporting environmental assessments. Next is unmanned aerial vehicles. You might hear, still on the same slide. Unmanned aerial vehicles, unmanned aerial systems, or drones. You'll hear them called all different things, but they provide, as you would expect, our aerial insights. This is great for monitoring birds, even marine mammals from the air, coastal erosion, while also contributing to surface level metocean data. The next platform that we will be looking into is remotely operated vehicles. These are subsea and again can offer detailed seabed mapping, environmental sampling like eDNA, in addition to infrastructure inspection and maintenance in the later stages of the offshore wind farms. The next platform and the final one I'll be discussing is uncrewed surface vessels, unmanned surface vessels. These really bridge the surface and subsea monitoring, enabling large area mapping, metocean data collecting, wildlife tracking, and together these robotic systems provide a comprehensive, efficient, and scalable approach to offshore environmental monitoring. Again, it's a short presentation. If you do want to dig into any deeper, feel free to put any questions in the chat or follow up. Next slide, please. Well, we've explored the robotic platforms that are relevant to the Accord program. So now let's try and highlight why they offer a major advantage over traditional methods in accelerating the consenting process. First up, obviously, is volume. So these platforms can collect significantly more data, larger areas, longer durations. Next is the velocity. They can operate faster, shortening the environmental survey timelines, which, again, crucial for us with our 7 years compared to, other countries and their consenting and commissioning process. Next is veracity. They can improve data accuracy. Honestly, that's often thanks to the sensor payloads and the algorithms that the previous speakers and the next speakers have mentioned. But yes, they do benefit veracity. Access is also a key, especially as we move into deeper waters, which are really enabled by these floating offshore wind platforms. So these platforms can operate often in deeper, harsher environments and all year round in comparison to traditional crewed vessels. Likewise, safety, they reduce human risk by minimizing offshore exposure. We also hope they have an environmental impact, low carbon and non-invasive, again, in comparison, aligning with our sustainability goals and our 2030 emissions target. And finally, cost. Such platforms often optimize efficiency, so there's a potential to reduce fuel, labor, and equipment costs. Next slide, please. Like any technology, there are always limitations and challenges we must overcome, as well as regulatory considerations. So again, with the time limit, I'll just highlight a few of them, but again, feel free to pop any further in the chat. I'll start with UAVs, and this includes vertical takeoff and landing, fixed wing systems, and different forms of rotary systems. So depending on that type of UAV, there may be some limitations. Firstly, with all aerial systems, there's always that trade-off between flight endurance, the payload, and the energy consumption of that. Obviously, you've got the offshore weather conditions that add further challenges. We've got strong winds, we've got rain, we've got salt spray, all impacting performance of the system. But if you're flying within visual line of sight, that can also be a challenge for the pilots. In terms of other challenges, launching and recovering UAVs from offshore platform or vessels can be difficult, especially in high sea states. Data transmission is another hurdle, but I'll leave that for my colleague later in the presentation, Rajesh. Finally, on the regulatory side, UAVs obviously must comply with airspace restrictions. A big topic within this area has been flying beyond visual line of sight, which at the moment you still have to go through a process with the UK Civil Aviation Authority to either get temporary or join one of their sandbox initiatives. However, again, this is a topic that is being pushed forward by the UK Civil Aviation Authority. Last year, they published their roadmap. This included 2 critical milestones. One, they wanted to demonstrate BV loss activities all of last year. And actually by 2027, they want to establish routine BV loss. In line with this first critical demonstration milestone, the UK had leveraged its sandboxes last year, which is, controlled testing environments designed to foster collaboration between innovators and regulators. Among 6 BV loss projects chosen for last year's sandbox, it was actually a UK UAV developer air inspection and supported by a world-leading offshore wind developer. So I think we're all very excited to hear about that. And also that wind farm spaces will be classified as atypical airspaces. So again, we might have less BV loss restrictions. Next slide, please. UAVs, again, like any platform, they can face that endurance versus payload trade-off. Some USVs can operate offshore for months, but sensor selection impacts power consumption. High power sonar and hydrophones drain energy faster than low power sensors. Another one may be operating in high sea states or strong currents. That can always limit deployments or power consumption. Collision is another risk of concern. So USVs must navigate safely around vessels, infrastructure, and marine. Sorry, I can't see anymore. On the regulatory side, the MCA has introduced USVs specific code into Workbook Code 3, providing a clearer framework for compliance. Additionally, last year in August, there was that mini MAS exemption, but it was, to reduce the certification burden for autonomous vessels under 2.5 meters. But, despite the challenges, recent regulatory shifts signal growing acceptance of autonomous surface vessels, paving the way for a wider adoption in offshore wind monitoring. Next slide, please. And the last limitations I'll talk about is subsea robotics. So in this one, I'm including remotely operated vehicles, autonomous underwater vehicles, the likes. Again, with great variation between manufacturer design, I'll just discuss some potential limitations that may be faced. For AUVs operating at depth, real-time data transfer could be limited, acoustic communication is slow, power constraints, so optical methods have short ranges. Biofouling may present another challenge, and of course, navigating complex subsea environments. On the regulatory front, while there are currently no direct governing subsea operations like the airspace or the surface water like we've discussed, industry standards still play a pivotal role. You've got entities like the American Bureau of Shipping, they produce technical guidelines, and they've actually started doing certification for ROVs doing hull inspections. So we expect that to move into other sectors. Next slide, please. And we'll go to the next slide again, please. When we talk about environmental monitoring in offshore wind farms, it's not just about the robots themselves, of course, even though I'm a robotic developer. The robot platforms are a means of physically collecting the data. They enable access to areas that would be difficult, dangerous, or inefficient for humans. But it's the sensors which are what actually gather the environmental data and improve the performance of the robotic platform. But finally, what brings everything together is that capturing the data is only half the battle. The real value comes from how we process, analyze, and store it. Advanced machine learning models can extract trends, detect anomalies, and improve predictive capabilities for offshore ecosystems. Essentially, robots provide mobility, sensors provide insight, and data provides intelligence, and together they form a complete system for effective environmental monitoring. Next slide, please. So that brings me to section 2. Next slide. So you've already saw a map of our locations throughout the UK. The ones on this map are really the ones where we have nice testing assets or demonstration sites for our robotic developers. The hub of our robotic activity is definitely, I would say, our Dare Centre in Blyth. Next slide, and if you can just play that video, it's a 30-second video of the Dare Centre. Thank you. I'm not sure if you can, well, there's text on the screen or hear the audio, but yeah, essentially we've got these 3 docks, all slightly different. One of them actually has a seabed, so you can do like cable trenching and so on like that. Another one has cables and a monopile, so you can do asset inspections. And the other one has a sensor suite, so you can manipulate the environment as well. So we've got like turbidity, lighting, and so on. Yeah, you can see the one there. So yeah, really lucky to have this asset, as well as like a dedicated area for the developers to use, like a control room that's hooked up. Again, for like the aerial side of things, there's also towers, and we have access to this river here, which then goes out to our NOAA Met mast. Next slide, please. It's really important as a catapult that we're able to support the supply chain as you move throughout the technology readiness level. So again, if you've tested and validated at the Dare Centre, if you're at the stage after that, we again want to provide assets. We do have our very own offshore wind turbine, but it's actually connected by a 20-meter bridge, but still offshore. You can still do foundation inspections when it's at high sea. So that's just up in Edinburgh, but we do have access to other sites such as the NOAA Met mast. And also, if you go to the next slide, we're in a partnership for the Humber portal. If you can click a few, so the next boxes come up, please. Yeah, at the Humber portal with our partners, we've got access to doing testing and validation within the port. We've got a research buoy, which gives you 5G access. And then again, at the discretion of our partners and approvals, we can get access to wind farms. If that's something that you need, I've got a dedicated colleague that his job is to ensure that developers, aren't limited by things like this. So do get in touch if you need access to this higher TRL testing and validation. Next slide, please. So that brings you to the virtual offshore wind farm that my team are currently developing. So I want you guys to really understand the need of this, which we are calling virtual Dare, like virtual Dare Centre. So I want you to imagine that you are a robotic developer. If you're having trouble doing that, can you press next? On the slide, please. I asked ChatGPT to create an image of a robotic developer at work. So this is who you imagine you are. Have to say I was very offended. You know, what's the need for the bow tie and the Rubik's Cube? But I digress. So you're a robotics developer. You've found a problem. You've designed a robot to meet this need. So for example, it could be you want to do drone inspections around an offshore wind farm. And now you've built it. You need to test and validate it. One, you need to see if your system actually works as it says it will. And then secondly, you need to ensure that it will work in these harsh offshore wind environments. Next slide, please. Our other challenge in the offshore renewable sector is that for robots to be adopted, there usually has to be a cost-saving benefit. Ultimately, what financial models in our sector show is that ROI will be maximized when we can deploy heterogeneous multi-fleets of robots that work together symbiotically as a team. So we also, on top of needing a way to test them, test how they work in these extreme environments, we also need a way to allow different robots from different manufacturers talking different languages to come together and work together as a team. Next slide, please. So our solution for that is VDARE, of course. So essentially, this is an offshore wind farm simulated environment. We've got different simulations for you. We've got, for example, a floating offshore wind turbine. We've got different fixed wind turbines. We've got multiple wind turbines together. And we also, you're able to manipulate every environmental condition from currents, the wave height. Also, all the assets are also kinematically correct. So the wind turbine blades are really spinning. They're really creating turbulence. So if you put your drone into our environment, you're going to have to overcome that, as well as the environmental conditions. So we really want a way to put your robot through the paces. Again, another key feature is we are working on a way to allow robots to from different manufacturers to communicate with each other. So at the moment, that's just like low-level control. You're able to send your position or IMU data and things like that. You're not sharing data, but you're sharing sensor positions. But that's the aspect that we're currently developing, also making it available for hardware in the loop testing. Next slide, please. Again, being a virtual asset, we're hoping to provide affordable testing for developers throughout their TRL journey and enable that iterative design testing. We aim to build trust and assurance and a way developers can test their robots in a virtual offshore wind farm, then progress. Like I've said, we've got the DARE Center, we've got LDT, we've got offshore assets. Final slide. If you can move on. Yep, excellent. So yeah, really excited about this project I'm currently working on. We've got fantastic partners. We've got Bow and we have Aqua Ocean. This is putting VDARE to the test. So we've got Aqua's hydrogen USV. We're integrating it with a UAV and an ROV. Bow have a fantastic communications layer, allowing for that interaction between robots that are not all open source. So you can share positions, you can share data and so on. And we're currently putting that to the test in this experiment. That's pretty much me. So last slide. My contact details are here. I'll also be here during the presentation to answer anything on the chat. I'll now hand over to Dr. Tom Culverhouse of Sonardyne. Thank you.
Hi, thanks, Melissa. Good morning, everyone. I'm Tom. I'm going to be talking about our Sonardyne Origin 600 ADCP in a bit more detail and how it can help with environmental monitoring. Next slide, please. I've got a content slide here. I won't stay too long in here. Be assured there's a beginning of this talk and an end, so we can skip to the next slide. I'm sure many of you are familiar with ADCPs, but I'll just very briefly go over how they work. They use acoustics, use sound transmitted into the water to measure currents as a function of distance away from the ADCP, and they can measure those currents repeatedly with respect to time, so you can track change. So the bottom two plots on the left-hand side, we've got time on the x-axis, those are repeated measurements, and on the y-axis, we've got depth above the ADCP. The sort of line near the top is the sea surface. And this plot shows backscatter intensity, so how strong the signal is that the ADCP receives. And you can see from this data, it's quite good for tracking things like sediment motion and effects like scour. On the right-hand side, you've got the same kind of plot, time on the x-axis, depth on the y-axis. And this is showing the eastward velocity component. And this is showing the currents, how the currents are changing as a function of time. And on the left-hand side, you can see we've got eastward velocity in the sort of yellowy color. And on the right-hand side, the tide's changed. And you've got dark blue, which is a more westward velocity. So these devices are great. You can use them for all sorts of things, and particularly for monitoring applications around offshore sites. They're great for consenting, characterization, operations, but also other sophisticated underwater hydrodynamics measurements, such as turbulence, mixing, and stratification, which, as Benjamin and Beth mentioned earlier, obviously affects the marine life. Next slide, please. So our ADCP does all these things very well. These are the sort of basic things that you'd expect any ADCP to do. I won't go into too much detail, but we can measure waves and turbulence with this device. We can measure currents, obviously. We log standard PD0 data formats, and we provide supporting software. Next slide. Some of the neat features. Sorry, can you go back one? Yep, there we go. We've got an internal rechargeable battery. That's quite nice. You never have to expose the electronics to recharge the device. We've got proprietary data formats. We'll talk a bit about those later. And we've got a huge amount of internal storage, so we can log not just the acoustics from the ADCP, but also any external sensors you might have plugged in. And again, we'll talk about that momentarily. Next slide, please. Okay, but USP number one for Origin is its integrated acoustic connectivity. And those of you familiar with Sonodyne will know that acoustics are our bread and butter, acoustic comms and positioning. And this is neat because it allows us to control the ADCP remotely. So for example, if you're doing a site characterization operation and everything has to stop for whatever reason, you can tell the ADCP to stop too, which means that you're not burning battery, making measurements that you don't want to make. So you can keep the ADCP in the water for longer, lowering cost and improving efficiency. The modem's compatible with most of our topside transceivers. So there's a topside transceiver out there for you doing your acoustic comms with our ADCP. And you can also use the ADCP itself as a positioning beacon for our ultra-short baseline USBL positioning systems. So at worst, you'll get spatial resolution of about 1 meter as to where the ADCP actually is. And in many cases, you'll get better than 1 centimeter. So this is really good for things like mapping data you collect to digital twins. And you can tie the simulations together with real-world measurements as well. So that's really good. Next slide, please. And then we've also got onboard edge processing, which is where we take the huge amount of data that ADCPs tend to produce. You can see an example on the lower left. That's a gigabyte or so of data, and we can deploy processing algorithms onto the ADCP that transform that data into something more informative and also much smaller. So in this example, we've got 1 gigabyte or so of ADCP data being processed into waves parameters on the lower right, and that comes out as about 100 bytes. So you've got a 100,000 or so factor of compression there. And best of all, you can extract that data to the surface acoustically because it's small enough. So you don't have to rely on the short range and high power optical comms. You can get it all through our acoustics using the same transceivers that you use to control the device as well. So you don't have to have a buoy there permanently to take this data in real time, although you can. You can also harvest the data using USV operations or AUVs. Next slide, please. So just a bit of baseline performance. Here we are. And I should say in all these plots, we're comparing an Origin 600 in purple with edge processing to a reference ADCP from a different supplier using offline processing after the device has been recovered from the water. On the left, you can see the current speed at the top and then the current bearing, and you can see the two ADCPs match very, very nicely. And at the bottom right, you can see waves parameters, so that the upper plot is significant wave height, which obviously affects crew transfer operations. And so, so all this data can be accessed in real time or harvested through the acoustic modem. So you can get faster insights into what's going on at your site, which may help to improve and speed up the consenting process. So hopefully that's useful. Next slide, please. Right, so that takes us to where we are about now. What's coming up in the near future? So Scooby-Doo wanted to know, so I thought I'd put a few slides in. If we could go to the next one, please. So what if you want to sample for months and months and months? Yes, you're going to need an additional battery pack. So this is one on the left-hand side. This is just a schematic. But like the internal origin battery, this one is going to be rechargeable. It will triple the length of your deployment. And it can also report its charge status. So you always know how much battery charge is left in the device, and you can access that data acoustically. And so you can have a really good insight into when it's time to bring everything out of the water and recharge. Next slide, please. So in addition to that, we wanted to provide the technological capability to provide a more sort of holistic viewpoint of what the ocean's doing. And this is where our battery multiplexer comes in. So it contains the same batteries as the device you can see on the left, but this one also has 4 ports for external sensor payloads. So you can have a CTD, for example, an SV sensor, turbidity sensor, all pre-configured and feeding data into our multiplexer. And then this data is streamed out of a single connection into the ADCP where it's logged and can also be fused with the ADCP acoustic data. And so you can have not just acoustics, but all variety of sensors, payloads being fused together inside the ADCP edge environment and exported to the surface acoustically. So you're not just restricted to ADCP data. You can plug in all sorts of third-party sensors into this device, and if you want to leave your ADCP down for years at a time, you can actually daisy chain 3 of these devices together, and they'll sit there running for as long as they can last. So hopefully that will reduce the number of times you have to engage in sort of costly and potentially risky recovery operations. So I've talked about a lot of kit. But that's a lot, a few different cables to plug together, and other bits and bobs that you normally need in a deployment. If you can go on one click, please. So what if you want to wrap that up in a turnkey integrated payload? So we've developed a lander that can do this. You've got the ADCP in the top left in the diagram. What you can't see are the 3 batteries underneath, but you can see a little turbidity sensor that's plugged into our multiplexer. So that's the little gray, black tube with a red connector on the end. And we've also got an integrated release mechanism that you can see there. There's the acoustic transponder and a pop-up buoy. And there's underneath that, there's a rope canister. So you've got everything you need in one payload to plop them down on the seabed and receive all that nice oceanographic data coming back to help with your operations. So those we supply as well. Next slide, please. Okay, and just to sort of convince you that this isn't just designs and things on paper, here's a couple of devices that have seen some action. So we've got the ADCP bed frame deployed with a full payload at the bottom left there, and we've been working quite hard with numerous deployments and applications over the last 12 to 18 months to show what this sort of kit can do. Next slide, please. Okay, so what other features are we bringing out? So the industry standard PD0 format is shown on the left-hand side. So this is backscatter intensity data, so how bright's your signal, and the bin size on the vertical axis is about 0.5 meter. So that's typically the maximum resolution you'll get out of other ADCPs. If you could click on one, please. This is our proprietary AGRAM data. So this is data captured from the exact same deployment at the exact same time. But you can see, although the vertical resolution of the features in the water column itself isn't better than PD0, the fidelity with which we can display them is. So if you're interested in things like mixing and stratification and surface waves, for example, you can actually find out where those boundaries are at a factor 10 or 20 times better than you can with conventional PD0. And with this data, you can also obviously get the current information that you want to be able to measure currents and waves. And if you can click on an extra one though, please. So our new feature is going to be an echo sounding mode. So this is a mode where we send a different type of pulse into the water, and it flip-flops between the ADCP type pulses that measure currents and these echo sounding pulses, which can measure structures at much finer scales. And you can see that the difference on the right-hand side. So if you can click on one, we'll see an example of that in action. So this is some data we captured last year at an aquaculture site as it happens, but you can see all sorts of interesting things going on here, sort of the impact of surface waves sort of causing bubbles and nucleation down through the water column, and then lower down you can actually track particles as they're scattering off the acoustics in the water, so you get additional insights into the hydrodynamics this way, alongside doing the standard ADCP Doppler measurements that we can do. If you can go to the next slide, please. So because we're seeing this world of hydrodynamics and ecological and biological worlds all come together and fuse, we can do that kind of thing with our echo sounder mode as well. So here's two examples of schools of fish which look like they're feeding on layers of perhaps zooplankton or other biological matter in the water column. And so we can do this with our ADCP, as I said before, interleaved these echo sounding style pings and getting the hydrodynamics from the current measurements at the exact same time. So that's really hopefully quite powerful. And again, will hopefully help provide a more holistic picture of these offshore floating wind sites that we're keen to progress. If you could go to the next slide, please. So that's a summary. I'm just about out of time. That covers everything I've said, so we can go to the next slide. And what are you doing next? So we're always seeking to innovate and do new things that can meet the challenges that floating offshore wind and fixed offshore wind is facing. So we've got our engineering teams developing next-gen products. We've got data scientists working on algorithms and data processing to make the edge environment that we've got deliver more value faster for these sorts of applications. And we've got 2 PhD students working on the application of Origin ADCPs in offshore renewables. So one in wind and one in tidal. And we've got a bunch of summer students that come in and help us de-risk the long-term crazy ideas we've got to help support everything that's going on in ORE going forward. Thanks very much today. That's the end for me. And if you want to get in contact, if you go to the next slide, very happy to take questions. Thanks very much. And I'll hand over to Nikki Harris from SAISH.
Hi. Thanks, Tom. So I'm Nikki Harris. I'm an Associate Director of Environmental Services at SAISH. So we're based down in Devon, specialising in underwater noise and marine mammals. So next slide, please. So the previous presentations have set quite a nice scene. If you just want to skip through some of this, I think just fill up the slide is fine. I think particularly Caroline set the scene quite nicely in terms of what's needed in order of speeding up consent, and Melissa's done a fabulous job at explaining really a lot of the benefits to autonomy and what it can achieve. So, you know, being able to get data in real time, you know, in this day and age, we want everything now, and marine survey is not any different. Obviously there's cost efficiencies, we can speed up, we can go into much more extreme remote environments. I think one of the other areas we maybe didn't touch on is some of the flexibility and adaptability of autonomy. So being able to deploy and recover some of these smaller USVs, we can do that quite quickly. We can optimize being able to go out and collect data maybe more efficiently and quicker than we can by having to get a vessel ready and a crew mobilized. So I think we've covered all those quite nicely. So I'll move on to really delving into some of what options of autonomy there are and what types of autonomy are available. So autonomy is obviously the use of systems and technology that performs tasks in the marine environment, removing that element of human intervention. So the systems range from remotely operated vehicles through to fully autonomous vessels. And I think we've covered quite a lot of the platforms already. Melissa covered some of the, you know, the USVs, UAVs, all of those were drones. So I won't go through all that. Maybe touching more on some of the sensors that are really playing some of that part in marine autonomy. There's a whole range of sensors being developed, and it's amazing to see how we can kind of bring those together to provide a really big picture. So we've got sonar that can obviously look at the seabed, optical sensors for visual observations, chemical sensors for monitoring water quality and pollutions, and environmental sensors for collecting some of that background temperature, salinity, current information. Data collection, will obviously British will cover up some of that, I'm sure, in the next presentation, but there's obviously a range of data, and I think that's really where you have a real understanding about what we're trying to achieve in our marine survey or the monitoring that we want to do. So we can either collect data from those sensors and post-process, or that data can be used to be transmitted in real time or processed and parts of it being used. So there's a lot to be looked at in terms of when you're planning environmental monitoring as to what kind of data we need and when we need it. The autonomy is developing all the time. It's one of the most rapidly developing technologies out there, I think. And we've got a whole range, really, depending on how much human interaction we need through that. So the augmented autonomy still needs some human assistance. We've got semi-autonomy, which is enabling systems to happen autonomously, but potentially with humans checking it over or providing oversight or QC, through to full autonomous systems that can operate completely independently, send the data where it needs to, and humans are not required. So the point of my presentation, I really wanted to kind of take this chance really to kind of share a few real life case studies of how some of this technology has been used, particularly in the commercial field. So I'm going to go through some using different sensors, different types of data transmission, and using different types of platform. So the first case study I'm going to cover is using optical sensors. So these are effectively cameras mounted on, you can mount them on various different types of platforms. There's different types of camera systems out there. The one that we've developed generally fits onto a range of platforms on a vessel, and thermal imaging. And it has a range of uses. So it can be used to look out for obstacles in the water. Those could be fish aggregating devices, vessels that don't have AIS, that could be an obstacle, through to marine life. That particularly has a use in terms of being able to manage mitigation for marine mammals around operations that might be harmful, and that enables operators or onboard scientists to be able to implement mitigation measures around that. We're able to use them to track different types of marine life or vessels, being able to build up a picture of site usage. We can look at distribution patterns and be able to get an understanding about numbers of particularly of marine life that might be using an area. Sorry, if you want to skip on a couple of slides, we're on cameras. And the next one, sorry. Thank you. And on to the next one. And if you'd like to just play there's a little video on the next slide. If we can skip ahead. And basically, these camera systems are enabling us to be able to detect different types of obstacles in the water and classify them. And where machine learning is really starting to come into play is being able to teach the camera system and the software behind it what is the object that you're looking for, and what isn't. And actually, the what isn't is just as important as the what is. So being able to, particularly for the use that we use a lot of these cameras for, which is being able to detect marine mammals at sea, is being able to, identify a log is not a marine mammal. The machine learning aspect of it is pretty intense. We have to spend a lot of time teaching, feeding the camera system lots of different video systems, being able to show what is a marine mammal. Is the video playing? No. And basically, it teaches the software to put a probability to what is a marine mammal. Here we go. So it's this is using our thermal imaging system. So it enables us to be able to look for marine mammals at night in dark, poor visibility. And it identifies what it thinks is an object, and it applies a probability as to whether it's going to be, it thinks it's a marine mammal or not. And you can set automated detections for that. So if it reaches a certain probability, it will send an alert. And this is as we're moving into being able to replace that human interaction, or at this stage, it's still very much wanting that human validation to it. So that's one of the case studies. If we could move on to the next slide, please. The next case study looks at different ways of transmitting data, getting towards that real-time capability of monitoring noise. So traditionally, particularly for monitoring a lot of offshore operations, it's done post-processing. So we deploy autonomous recording units and we collect the data. We have to go back out on a vessel, recover them, and process the data to get the information that we're looking for. This system that's been developed is looking at real-time sound measurements. So we're able to get real-time understanding about what the noise levels are of various things. And that could be offshore pile driving during offshore wind farm construction, could be looking at noise levels from vessels utilizing the area. We could look at soundscapes and just the background noise levels. So really anything that's making noise in the environment, we can detect that and stream the data. One of the biggest issues with real time is really the transmission of data, and I think many of you on the call are aware of how much the restrictions are in terms of and the limitations of streaming data. So by being able to process some of that data on board our platforms, we're able to stream not the whole spectrogram or the whole data. We're able to actually just identify the key criteria and pass that on. If you could move on to the next slide, please. So for example, in this case, we've been looking at particularly pile driving activities. So we're able to get the system to process the key metrics that we're looking for. So that could be sound pressure levels, peak to peak, sound exposure levels, different octave band measurements and pulse length. And we can identify the different criteria we want the data is processed on board. And it's just those little alerts with that data packages sent to anywhere in the world, really, over particularly now we've got a lot more satellite capability. So we can process that data on board and send it to maybe the piling vessel, for example, in the case of piling, or to our offices to and that's really enables us to be able to make much more speedy decisions. If we could move on. So for example, in the case of offshore wind farms, where we can deploy these buoys around construction activity, we can really get an understanding of what the noise levels are of piling particularly. And this is going to be something that's going to be quite key as we're looking to move more into having a decibel limit for pile driving activities, potentially in English and Welsh waters fairly soon. So for example, just to see if anyone is still awake and needs a wake-up call. If we just want to play the sound clip. If it plays, we can get a just get a snippet of what we can hear. I'm not sure the sound's working. That was going to be piling. So if you just imagine a lot of banging, that'll probably do it for you. So, and if we move on to the next slide, the last case study I'm going to share really is looking at a couple of different examples of using platforms. So the platform that we have used is the Autonaut, which is a USV. It's a bit different to some of the other USVs you might be aware of, as this one's wave propelled. So it really ticks that environmentally friendly box. So it harnesses the motion of the wave for its forward propulsion. So the advantage of that is obviously it doesn't have to come in to recharge or to refuel, so it can plod on for as long as it likes. So it's not a fast system, but it's great for that long-term environmental monitoring requirement. It has solar panels on the top, so we can plug it with lots of different sensors, depending, and produce a real package of what we want to do for a monitoring purpose. So there's lots of different case studies of use. This one is looking at, we've had a range of, I think 4 or 5 Autonauts bobbing around the islands of Barbados. An awful place to work, I'm sure, but basically collecting and streaming real-time metocean data to the meteorological center in Barbados. And the aim of that is being able to improve some of their hurricane warning systems by collecting a lot more data around what happens around the storms and the hurricanes, and being able to improve their alert systems. If we move on to the next slide, please. And finally, a bit closer to home, and maybe one a bit more closer to my heart with the marine mammals, is being able to utilize USVs for collecting marine mammal data. So again, this was using an Autonaut, which was deployed off the west coast of Scotland, and it was able to have a long endurance mission out to the Rockall Trough and down that west coast of Ireland, collecting some really interesting data, particularly beaked whale data, in more kind of frontier areas. So it really showcasing how some of these autonomous platforms can really go a lot further and into more extreme environments and collect data that potentially for vessels would be, hugely expensive and quite difficult in order to manage crews going out that far. So this was 115 days of surveying and collecting a range of environmental data alongside marine mammal data. And that's it. If we move on to the last slide, just a quick thank you. Obviously, there was a lot of people that are involved in these technology developments who have been referenced on the slide. So a big thank you to those collaborators, partners, and companies that allowed us to test our equipment on their projects. So, you know, this technology doesn't happen in isolation. So I think that's something we've all learned today. Thank you. And I'll hand over to Brijesh of Ori Catapult.
Thank you, Nicola. And good afternoon, everyone. So being conscious of time, probably I would just like to go through a couple of slides, which are really very important from the data architecture perspective. So thanks to everyone who have presented before me and have set up this stage, like, so that I don't need to repeat a lot of things in there. So Sarah, if you can just go on to the next slide, please. So as you can see, my name is Brijesh Suryavanshi, lead data engineer with Ori Catapult. And with the Accord project, my role is to take care of the technical delivery of the analytics platform, the advanced data analytics platform. So what is the objective here? To demonstrate how data analytics can improve informed decision-making, effective collaboration, and meet the regulatory compliances, like, to optimize the development of offshore renewable energy projects. Next slide, please. So I won't spend a lot of time onto this, but we have already seen what is the problem statement, right? The complex and data intensive consenting process. The companies, the wind farm developers, they are like, performing all these activities in silos, a lot of data being collected in silos, right? There are inefficiencies in the way the regulatory processes are being followed, and then handling diverse environmental data sets there, right? So what can be done in order to address this problem? Next slide, please. Okay, so the solution looks like an unified environmental data platform, right? A centralized hub for collecting, managing, analyzing, and sharing data. The idea is, why don't we develop a large scale, high resolution web portal, which should contain, like, the EIA and monitoring data of all the offshore wind farm and grid projects, right? So usually whenever we talk about developing the data platforms or the analytic platforms, there are some core components associated with that, right? How do we ingest data from different sources? How do we store that data efficiently, right? How do we run processing onto that data and analyze that data? And then there are other aspects as well, right? How do we develop APIs and integration layers so that the third-party applications can connect to that application? And then how do we develop visualizations, right? Or the access mechanisms on that data. So next slide is going to tell us, like, a very high level data architecture, what we have in our mind right now. So next slide, please, Sarah. So if the one previous to the previous one, Sarah, not this one. Yes. So this is a very, very generic platform architecture, what we have in our mind right now. And this is subject to change depending on, like, what exactly do we want to develop, depending on the requirements when we are going to gather them, right? So some of the key components in that is, like, infrastructure. What should we have? Should we have an on-premise infrastructure or cloud? But looking at the kind of data coming our way, like, the big data, what Melissa was talking about some time back, like, the three V's there: velocity, volume, and variety of data, right? So the preference would be cloud. Now it's yet to be decided whether that's going to be AWS, Azure, or GCP. But our expertise is in Azure, and that could be something which we would select in future, right? Then comes the management layer, wherein we talk about how are we going to govern that data, right? How the APIs would be developed, how are we going to manage the security on the platform, and then how do we monitor and administer that data. So if you look in the diagram, there are usually three partitions in any architecture, wherein there are data sources sitting on the left-hand side. So Melissa has already covered some of them in robotics section, right? Like the autonomous underwater vehicles, the surface vehicles, and then you have your IoT sensors, which, like, sometime back someone was talking about it, right? We have cloud applications there. The idea is not to reinvent the wheel or develop one more application, to host that data and present it to the end users. The idea is, why don't we leverage the data which is already available? Why don't we leverage the cloud applications like Marine Data Exchange, right, which is already available, and build something on top of which can help us solve some of the industry problems related to environmental impact analysis, and how do we accelerate the consenting process there, right? So usually you would have data connectivity there, you would have the data ingestion layer there, right? Then you need to have the data refinery, wherein you can think about how are you going to integrate the data, how are you going to store that data, right? How are you going to run the pre-processing on the data? Because many times you cannot just simply start working onto the raw data, right? You need to get that data, process it, and keep it ready for the analysis purposes, right? And to the right of it, if you see the analytics platform, how are you going to access that data? What tools and applications do you need to access that data? And if it comes to any kind of machine learning algorithms, what tools and techniques would you have in that platform, so that you can start using that data for different purposes? And to your extreme right, you can see the business users, the people or the users who are going to be benefited by using this application, right? So there would be developers, Crown Estate, UK Gov, SNCB, academia, stakeholders, different stakeholders. So all the people, they can use this centralized web portal, which can address a lot of challenges or problems what they are facing right now in consenting process, right? So next slide, please. So this is how the data would flow. This is the same thing, on the left hand side, you can see all the platforms which are going to generate the data. Then there are different data types highlighted in that amber color, right? You would have text data, all three types, structured data, semi-structured data, unstructured data, right? So whatever is the data type, we are going to capture it, we are going to store it, we are going to process it, and then we are going to present it to the end users, right? So that's going to be the Accord high-level data flow there. Next slide, please. So yeah, so some of the key benefits, well, faster approval, reduces delays and save costs, right? Improve transparency among stakeholders. What are the environmental insights? Well, data-driven decisions mitigate risks, right? There are a lot of risks which we are facing right now. It supports sustainability through monitoring, right? And then the regulatory efficiencies. Streamlined data sharing accelerates permitting, right? So these are some of the key benefits what we can achieve using that data platform. Next slide, please. So just a quick real world example. So just imagine developer submits a wind farm application, right, to the authority. Then rather than going for a specific survey, conduct the survey, collect the data, and then start analyzing it, we would have the system already in place, right? Continuous monitoring and collecting data onto this platform. So regulators use the platform to access geospatial and biodiversity data there. And then approval time is reduced by 30% compared to traditional methods. Now, 30%, this is what I've got to know from the experts. But the success of any project is always gauged with the quantifiable benefits what we can achieve, right? So that's something what we can achieve using the data analytics platforms in this case. Next slide, please. Sarah, could you please go on to the next slide? Okay, so quick recap. Well, simplified data processing using the advanced techniques, right? Enhanced collaboration between the different stakeholders, and then finally the accelerated consenting. Yep. So I know it was pretty quick, but keeping time in mind, I had to just give a quick update on the data architecture. With that, I would like to hand it over to Julie. Julie, over to you.
Thank you very much, Brajesh. We are slightly over time, so I will keep this brief. But first of all, I must say thank you so much to all our speakers for keeping to time and putting so much content into this webinar, which has been brilliant, and I'm sure will raise a lot of questions. I think we see there is an overwhelming case for a regional ecosystem approach, both in terms, as Beth said, of its predictability and the fact that it has reduced complexity. There's an overwhelming case for using innovative technology. That's carbon reduction, cost reduction, time, and most importantly, greater certainty in the data, greater veracity. We've seen the technology in use from Tom and Nikki, real world applications. It's actually happening now. This isn't just something that we're seeing in research. And as Caroline and Beth say, the science is ready. So let's get moving. thank you for joining us. Thank you for sticking with us. I really would suggest that people join the Celtic Sea Supply Chain Cluster if you haven't already. There's a link there on that slide, or just Google Celtic Sea Cluster, and we can keep you up to date with movements on this project and other projects to do with floating offshore wind. So thank you so much, and we look forward to further questions and interactions from you. Goodbye.